So in the previous section, we have discussed about the polar representation of a complex number. So now we come to the third form of representation of a complex number, and this is called the Euler's form. So if we consider the polar representation of a complex number z, which is given by z is equals to r multiplied by cosine of theta plus I sine theta, then this particular section, which is cosine of theta plus I sine of theta, can be written as e to the power I theta. So there's our complex number z becomes r e to the power I theta, and this way of representing a complex number is known as the Euler's form. So this is the Euler's form. So let us do a quick problem. So let's say we have a complex number z given by 1 plus I. So we'll go the usual route of finding r. So r will be simply the modulus of our complex number z, which is 1 squared plus 1 squared, and we take the square root of it. So that gives us square root of 2. Then to find out theta, first we find out the angle alpha, which is tangent inverse of the absolute value of the imaginary part divided by the real part. So this is equals to tangent inverse of 1. So we have alpha is equals to tangent inverse of 1, and we know that tangent of pi over 4 gives us 1. So we have alpha equals to pi over 4. Since the real and the imaginary part are both positive, so our z lies in the first quadrant. So it lies in the first quadrant. So that means our argument of the complex number z is simply going to be equals to alpha, which is equals to pi over 4. So we can now express the given complex number 1 plus I as square root of 2 multiplied by e raised to the power of I times theta, which is pi over 4. So this is the representation of the complex number z equals to 1 plus I in the Euler's form.